we like to describe this as an ordinary max-min problem where you do a procedure of finding whether gradient is equal to 0 and looking at the Hessian and seeing whether it's positive, definite, and so on, where you're not having to explicitly use any Lagrange multipliers. Or you're not having to solve actually, you're still going to solve the same system of equations as before, but at least you can use a second derivatives test. What we've talked about so far, you find Lagrange multipliers, but we haven't talked about how we can actually use anything like the second derivatives test to sort out maxes, mins, saddle points. So this method of Lagrange multipliers doesn't have that. So that's why we're going to adopt this point of view, trying to re-describe this whole thing as an unconstrained max-min problem. So we define a function h, and it's a function of x and lambda. So we have, it's a function of m plus n variables. And the way we define this function, it's going to be equal to f, and then we'll subtract from it a vector lambda. So this is a vector of Lagrange multipliers dot product with g. Okay. So finding a max or min of f subject to the constraints of g is the same as just finding the unconstrained max-min of this function. Why? Because if you look at the gradient of this and see where it's equal to 0, here's what we get. We get, so this is going to be a vector of n plus n components. So the first n components will just be the gradient of f. Wait, need a bit more room here. Minus lambda dot product with the Jacobian matrix of G. Okay. So that's the first part. The other part of the gradient is where, because here, these are derivatives with respect to the x variables. That's what gives us this piece. But we have these variables to consider too, the lambdas. So if we differentiate with respect to lambda, then this isn't going to give us anything because it doesn't depend on lambda at all. And this is a linear function of the lambda, so all we're going to get is minus g. Okay. Now, to find a max or min of this function, we need this entire vector to be equal to 0. So what does that mean? It means that this whole thing has to be 0. So g of x must be equal to the 0 vector. So we must have a constraint satisfied. So this function is designed so that that needs to be the case. And from this part, what we get is that the gradient of f must be equal to this dot product, which is lambda 1, the gradient of g1, plus lambda 2, gradient of g2, and so on, for however many constraints that we have. We have m of them here. But this is exactly what we came up with for how to find a constraint max min or f. The gradient of f had to satisfy this condition, and x had to satisfy these constraints. So we actually get the exact same system of equations to solve as when we described the method of Lagrange multipliers in the first place. It's just arrived at in a different way from the point of view of making the gradient of some function equal to 0. So now what you can do, though, once you find any x and lambda combination that makes a gradient of h equal to 0, here's what you can do. You can compute the Hessian, which is the second partial derivatives of h with respect to the x variables and the lambda variables. So you have to account for them both. So it's a larger Hessian matrix than if you were just finding an ordinary max min of f by itself with no constraints. However, one thing that helps you is if you're going to be taking derivatives, partial derivatives of all of this with respect to the x variables and the lambda variables, well, here we just have g of x. So these second partials with respect to the lambda variables are going to be equal to 0. So there are certain partial derivatives you know are going to be 0 no matter what your function is, no matter what your constraints are. And even here, this is a linear function of lambda, so you compute the partial derivatives of this with respect to lambda. This will go away, and you'll just be left with gradients of g. So yes, it is going to be quite messy, even if you only have a few variables, even if you only have one constraint. But this is something you can do in order to check whether any of these points that you find, any critical points with their Lagrange multipliers, you can check, are they, does this correspond to a max, a min, a saddle point, subject to the constraints. So this is just another way of looking at this method of Lagrange multipliers. And even though the system of equations you have to solve is exactly the same, at least this kind of viewpoint allows us to extend the second derivatives test to the constraint problem. All right. So this actually ends the first major portion of the course. There are 3 of them corresponding to the 3 chapters that we covered in Stewart on partial differentiation. Now we get into the second part where we deal with integration. So to refresh your memory from the single variable case, looked at the problem of computing the area of a region like this. So it's bounded by, up top, by the graph of a function. These 2 vertical lines, x equals a and x equals b, and down below by y equals 0. That way you go about it, you approximate this region by several rectangles, and each of them has a width delta x, and the height is dictated by the function. So if you're using some number of rectangles, n, then the area is approximately the sum of the areas of